Alright guys, this is our second video about reactions of organic compounds. Today I'm going to be focusing on reactions of alkenes. Okay, so the alkenes are much more reactive than the alkanes, which were addressed in the first video. Alkenes can undergo, most of these reactions are some sort of addition. Okay, and the idea is that when you have a double bond in a molecule, so let's say I have ethane, you can add some molecule XY and it can use the electrons from that double bond to form new single bonds. Okay, so that's an addition reaction. There's lots of different versions of addition reactions that we're going to go through, but this is the whole idea today. Okay, now there's this example described here of a bromination reaction. So we'll look at that when we get down to halogenation, which is our second example. Okay, so first example of a specific type of addition reaction is hydrogenation. So here I have some alkene. So I've got a double bond on there. Okay, and it's hydrogenation, which means that I'm adding hydrogen. And in the presence of a nickel catalyst, the hydrogen uses the electrons from that double bond to make new single bonds to hydrogen, and I end up with an alkane as a result. Okay, so here, if you wanted to practice your naming, you might recognize that this has 1, 2, 3, 4, 5 carbons. So it's pent, and then 2, because I would count from this side to get the smaller number, ene, and when I hydrogenate it, I end up with pentane. Okay, this is a reaction that's used on an industrial scale to take unsaturated fats, which will have double bonds in them, and convert them to saturated fats. Okay, obviously fatty acids are much bigger molecules than a pent-2-ene, but the same idea applies. Okay, so to convert vegetable oil into vegetable shortening, this is the type of reaction that would happen. Why might someone do that? The reason is because solid fats are more shelf stable. Okay, so if you're talking about like foods that you want to last a long time on the shelf in the grocery store or in your house, you might want to take your vegetable oil, which could go rancid, and hydrogenate it to make it into a saturated fat, which is much less likely to go bad. Next example is called halogenation. So this is like what was described up here. If I have some alkene, say I have propene, and I bubble it through a mixture of bromine, which is water soluble, and water, without the need for a catalyst or anything, just the fact that the bromines have lots of electrons that they want to make bonds with new things, my bromine will add itself across that double bond. So I'll end up with a bromine on the middle carbon and a bromine here. Okay, so your halogen will add again to the double bond. Okay. Another example here, we're going to talk about hydrohalogenation. So this is the same idea again, but now instead of having just a symmetrical like halogen molecule, we're going to talk about having a hydrogen halide. So something like, say, ethene, just going to draw it like that, with hydrochloric acid. So one of my carbon atoms is going to get the hydrogen, and then the other one gets a chlorine. So I started with ethene and I end up with chloroethane. Okay, so I added the HCl across the double bond. Now, when we're looking at an asymmetrical molecule that we're adding, we sometimes have to consider the different isomers that can form. Okay, so in this case here, I've got propene. Okay, and I'm going to add HBr. Now, ethene was a perfectly symmetrical molecule, so I didn't really have to worry about this. But with propene, it's not so symmetrical. The carbon in the middle has a different number of hydrogens than the carbon on the end. So when I add HBr, I actually have two possibilities. I could have the bromine add to the middle carbon and the hydrogen add to the end. So I would end up with this, which is 2-bromo propane. Or I might have the bromine add to the carbon on the end, this one right here. So that would be 1-bromo or just bromopropane. And I actually do have a rule that tells me which of those isomers is the major product, okay? So when I do this reaction, I'm probably going to get a mixture of these two, but I'm going to have way more of one of them. And I follow this idea described by a chemist named Markovnikov, so it's called Markovnikov's rule. And the way we often think of it is the rich get richer, okay? So if I have an asymmetrical molecule that I'm adding and it contains hydrogen, the hydrogen is going to go to the carbon that already has more hydrogens. Okay, and there is an explanation for this. I'm using this concept of what's called inductive effects. It goes a little bit beyond the scope of the SL course, but you can read about it in your textbook if you're curious. But the way we work this out, or just apply the rule without having to necessarily explain why it works, is I look at my original propene and I say, well, this carbon in the middle has 1 hydrogen, and this carbon on the end has 2. So if the rich get richer, the carbon that already had 2 hydrogens should end up with the extra hydrogen from the HBr. That's this scenario here. Okay, so that one's the major product. Okay, because my hydrogen here is going to go to the carbon, or is more likely to go to the carbon that already has more hydrogens. Okay, and then one more reaction with alkenes on this page, a hydration reaction. So here I have but1ene. I'll put the double bond here, so that's double bond after the first carbon. I'm going to add H2O, so water. And here my water molecule is slightly different from the molecules I've looked at so far because it's not diatomic, it's actually triatomic. But the water molecule is basically going to divide along sort of an imaginary line where we get a hydrogen adding to one of our carbons and then an OH adding to the other. Okay, so I'm going to have an OH adding to one of my carbons and a hydrogen adding to the other. Now, you'll notice, just like with my previous example, there are actually 2 isomers possible. My OH could add to this carbon in the middle of the chain, carbon 2, or I could have put my hydrogen on that carbon, which means that my OH, or my hydroxyl group, would have gone to the first carbon. Okay? And I can once again follow Markovnikov's rule to predict which of these 2 is more likely, or which one's going to be the major product. And once again, I want my hydrogen to go to the carbon on the end because it already has more hydrogens. The rich get richer. So once again, this is my major product. Okay, and I recommend that you go in and practice naming these two just so you have those skills sharp. Okay, so these are both butanols, but they have the hydroxyl groups in different positions, so you need to adjust the name accordingly. Okay, last type of reaction with alkenes, still an addition reaction, but this time it's a special kind of addition, very useful industrial reaction called polymerization. Okay, now you guys have seen polymers before because you've taken biology, so you've definitely seen proteins and DNA and lots of other very long molecules made up of repeating units. So this is an example of a synthetic, or how we make synthetic polymers like plastics. So polymers are made up of monomers. The monomers, if you're talking about a protein, are the nucleic or amino acids. Sorry, I don't know where that word went for a while. Okay, in the case though of simple industrial addition polymers, the monomers are all just simple molecules that have a carbon-carbon double bond in them. Okay, so you might have actually heard of plastics that are named polyester, polyethylene, things like that. Those are polymers with ester monomers or with ethylene monomers. So I will give you an example of a polymer here. So I'm going to actually show my formula for propene in kind of a weird way, just to show how this works. So propene, I've got my 3 carbons, and I've got my double bond between 2 of the carbons, okay? And I've just shown the carbon that doesn't have the double bond as kind of a side branch because it'll make it a little bit easier to draw my polymer. So if I just take a bunch of these and I react them with the appropriate catalyst and with some heat, then the double bonds will all break, so I can end up with a chain of molecules of repeating units. So see how this is the propene rewritten but without the double bond. So I think the electrons that made up that double bond can be used on either side to connect it to another propene. And I'm gonna draw a third unit here just to give you the idea. So this is three units of propene, but it could go on forever. Okay, polymers are really, really big molecules. This is just showing 3 repeating units. And this polymer, because it's coming from a propene monomer, would be called either polypropene or polypropylene. I'm going to write that in, polypropene. Or polypropylene is another way you might hear it referred to. Okay? So that's a polymerization reaction of a very simple monomer unit, much simpler than the amino acids that you've drawn peptide chains with before. Okay, so I'm going to cut it off there. I will include some practice questions and repost the PDF of this sheet if you didn't see it in the first post. And then I will make one more video, probably I'll post it on Friday, that deals with the remaining reactions on this page. Thanks a lot.